Somewhere in the constellation we call Leo, 124 light-years from where you are right now, there is a star that is smaller and cooler and dimmer than our Sun. For most human history, no one knew it even existed. But orbiting that quiet star, at a distance close enough for warmth and far enough for something extraordinary, is a world that has been keeping some astronomers up at night. Scientists believe this world may be covered entirely by a single global ocean. No continents, no beaches, just water, stretching to every edge of a world 2.6 times the size of Earth, beneath a green sky made of hydrogen. And if the most provocative data collected in 2025 means what some scientists believe it means, somewhere in that ocean, something may be alive. The instrument that found this signal is the most powerful space telescope humanity has ever built. And what it detected has ignited one of the most important scientific debates of the century. This is the story of a planet called K2-18b. And the question it is asking may be the most consequential question in the history of science. The central question is not whether or not this planet could support life. That is a question scientists have been asking for decades. The question that K2-18b forced into the conversation in 2025 is something far more immediate. Did we already find it? In April 2025, a team led by Professor Niku Madhusudan at the University of Cambridge announced that JWST had detected chemical signatures in K2-18b's atmosphere consistent with molecules that, on Earth, are produced exclusively by living organisms. The molecules are called dimethyl sulfide, and on Earth, they are only produced by marine phytoplankton. They are part of that ocean smell. And as far as science currently understands, life is the only thing that makes them. Every year, billions of tons of dimethyl sulfide rise from the Earth's oceans into our atmosphere, exhaled by the microorganisms living just below the surface. It is one of the most biologically active gases on this planet, and James Webb may have just found it in enormous concentrations on a world 124 light-years away. But almost immediately, other scientists started to push back, hard. And what followed was not just a debate about one planet. It became a debate about how much we trust our instruments, how we define discovery, and whether humanity is emotionally prepared to handle what we might eventually find. For most of human history, the question of whether other worlds existed was entirely philosophical. Ancient thinkers proposed the idea. Some were celebrated for it, others were persecuted. For 2,000 years, we had no way to know. Even after Copernicus and Galileo established that Earth orbits the Sun and not the reverse, the question of planets around other stars remained untouched. We had no instruments. We had no method. The stars were simply too far and too bright for anything orbiting them to be seen. That all changed in 2009, when NASA launched the Kepler Space Telescope. Its mission was simple, but audacious. Stare at one patch of sky continuously and watch for the faint dimming that happens when a planet passes in front of a star. Transit detection. A planet's shadow crossing a star's light, measured from 150 million kilometers away. Kepler found thousands of exoplanets this way. Most were gas giants, easier to detect because they are large enough to block more starlight. But among them were dozens of smaller, rocky worlds, and some of those orbited inside what astronomers call the habitable zone, the region around a star where liquid water could theoretically exist on a planet's surface. The habitable zone is not a guarantee of life. It is simply a set of conditions where life as we know it is not automatically impossible. It is, as astronomers often say, the beginning of the conversation. In 2018, NASA launched TESS, the Transiting Exoplanet Survey satellite, designed to do what Kepler did, but for the whole sky. TESS began building a catalogue of small planets around small stars, cool stars, dim stars, red dwarfs. And on that list, the system containing K2-18b became one of the most scrutinized targets in modern astronomy. For years, the scientific consensus around red dwarf planets was discouraging. Red dwarfs are violent stars. They flare constantly, releasing massive bursts of ultraviolet and X-ray radiation that, for planets orbiting close enough to be warm, would strip away any atmosphere. The habitable zone around a red dwarf sits much closer to the star than Earth sits to our Sun. For many scientists, close meant dead. The logic made sense. Red dwarfs are the most common stars in the galaxy. If life was impossible around them, that cut out the majority of potential real estate before we had even begun to look. The universe seemed less hospitable than we had hoped. But the logic had a flaw. It assumed that these planets had thin atmospheres similar to Earth's, atmospheres vulnerable to radiation. It did not account for something else entirely. What if some of these worlds were not rocky and thin-aired at all? What if some of them were mostly water? Some scientists began proposing a new category of world. They called it a Hycean planet. Hydrogen atmosphere on top, massive liquid water ocean below. These worlds, if they existed, might be resistant to stellar radiation in ways rocky planets are not. Their oceans would be deep and protected, and their size, significantly larger than Earth, would give them the gravity to hold onto that thick hydrogen envelope for billions of years. K2-18b fit the profile. It sits in the habitable zone of its red dwarf. It is too large to be purely rocky, but too small to be a gas giant. And when James Webb first looked at it seriously, what it found confirmed that the Hycean hypothesis was not science fiction. The atmosphere was real, it was complex, and it contained molecules that no one expected to find. The James Webb Telescope detects what planets are made of by watching them pass in front of their stars. As the starlight filters through the planet's atmosphere on its way to the telescope's instruments, different molecules absorb different wavelengths of light, leaving what astronomers call a transmission spectrum. Each molecule leaves a fingerprint. In 2023, JWST observed K2-18b and found something unprecedented. For the first time, it detected carbon-based molecules in the atmosphere of an exoplanet sitting in a habitable zone. Methane, carbon dioxide. These findings were confirmed. They matched predictions for a Hycean world. But in that same dataset, there was something else. Something faint, a hint of dimethyl sulfide. The detection of DMS in 2023 was weak, what scientists call a 2 sigma signal, meaning there was a 1 in 20 chance it appeared by coincidence. Interesting, but not convincing. Professor Madhusudan's team filed it away and went back to the telescope. They returned in 2025 with James Webb's mid-infrared spectrograph, a different instrument covering a different range of wavelengths. They observed K2-18b transiting its star again. And when they processed the new data and combined it with the 2023 observations, the signal for dimethyl sulfide rose to 3 sigma, a 0.3% probability of occurring by chance. The Cambridge team published their findings in the astrophysical journal Letters. Their language was careful. They did not say they had found life. They said they had found a signal consistent with molecules associated with life at a level of significance that warranted urgent follow-up. But the press release from the University of Cambridge called it the strongest evidence yet that life may exist on a planet outside our solar system. Within hours, the story reached the rest of the world. Within days, the scientific community began to respond. And within weeks, the debate had become one of the sharpest exchanges in recent astronomical history. Jake Taylor at the University of Oxford reanalyzed the same data and found that it was, in his words, consistent with a flat line. No signal. Kevin Stevenson's team at Johns Hopkins published a paper concluding that the mid-infrared data was plagued by red noise, instrumental systematics that could create the appearance of a signal where none existed. A separate team, combining all available JWST observations of K2-18b, found no statistically significant evidence for DMS or DMDS. The original team stood by their findings. They noted that their methods had been tested through independent internal analyses. They called for more telescope time. They were cautious, but they did not retreat. To understand why K2-18b matters so much, it helps to understand what it is. It is what astronomers call a sub-Neptune, larger than Earth, but smaller than Neptune. It is 8.6 times more massive than our planet, and 2.6 times its diameter. If you stood on its surface, if it has a surface, the gravity would be crushing. But K2-18b may not have a solid surface at all. Its interior may be an unbroken ocean, perhaps hundreds of kilometers deep, pressing down on a rocky core under pressures that dwarf anything in Earth's oceans. The Mariana Trench is roughly 11 kilometers deep. The ocean on K2-18b, scientists estimate, could be orders of magnitude deeper. The parent star, K2-18, sits in the constellation Leo. It is a type M2.5 red dwarf, cooler, smaller, and dimmer than our Sun. K2-18b orbits it once every 33 days. In comparison to our year, that is a very short orbit. But because the star is so faint, that orbit places the planet squarely within the zone where temperatures could allow liquid water. On Earth, dimethyl sulfide is exhaled into the atmosphere by marine phytoplankton. These are single-celled organisms, algae essentially, that live in the upper layers of the sunlit ocean. They are ancient, some of the earliest life forms on this planet. They have been producing DMS for at least 1 billion years. It rises into our atmosphere and contributes to cloud formation. It is, in a very real sense, life's most ambient exhale. The concentrations of DMS that Madhusudan's team inferred on K2-18b are thousands of times greater than what exists in Earth's atmosphere. If those measurements are accurate, and that is still an if, the planet would be producing this gas at a scale that dwarfs anything in Earth's biosphere. An ocean not just with life, but with life in extraordinary abundance. But here is where the scientific argument gets deeply technical. The concentration matters. Because the same tools that detected this signal, JWST's spectrographs, were not designed for this purpose. The telescope was built before the Hycean planet category even existed. It is being pushed to the very edge of what it was engineered to do. James Webb's MIRI instrument, the mid-infrared spectrograph, was calibrated for the wavelengths needed to study galaxies and star formation. Using it to hunt for trace biosignature gases in the thin atmosphere of a planet 124 light-years away requires what one astrophysicist described as pushing the telescope past its design specifications. That is not an accusation. That is simply the nature of frontier science. In science, a 5 sigma result means there is only a 0.00006% probability the signal occurred by chance, is the standard for claiming a discovery. The DMS detection on K2-18b reached 3 sigma. That is meaningful. That is not nothing, but it is not discovery. It is a lead. The gap between 3 sigma and 5 sigma represents somewhere between 16 and 24 additional hours of telescope time, according to Madhusudan's team. JWST is the most oversubscribed scientific instrument in the history of astronomy. Every hour of observation time is competitive, and K2-18b is not the only target. While the scientific community waits for more data, The question that cannot be avoided has begun to surface in ways that go well beyond spectral graphs and sigma thresholds. Here is the complication that the DMS story cannot avoid. In 2024, researchers found dimethyl sulfide on comet 67P Churyumov-Gerasimenko, a comet, an object with no ocean, no biology, no possibility of life as we understand it. This single finding shattered the assumption that DMS requires life to form. The comet discovery did not disprove life on K2-18b, but it did remove DMS from the short list of molecules that are uniquely biological. If a comet can make DMS through abiotic chemistry, chemistry that requires no life, then what exactly are we looking for on K2-18b? This is the fundamental challenge of biosignature science. A biosignature is only meaningful if we can be reasonably certain that the molecule in question cannot be produced by non-biological means at the concentrations observed. For DMS, that certainty no longer exists. The field is still working out what, if anything, could produce DMS in the concentrations claimed for K2-18b through purely chemical means. Scientists at several institutions are now running experiments to determine whether the hydrogen-rich atmosphere of a Hycean world could produce DMS at the concentrations JWST inferred through photochemistry or other abiotic processes without any life involved whatsoever. The results of those experiments will determine how to interpret everything that comes next. And here is the deeper problem beneath the problem. Even if the DMS detection is confirmed to 5 sigma, and even if abiotic chemistry cannot explain it, what we would have is not proof of life. What we would have is a molecule that is currently associated with life on one planet, ours, detected on another. That is a hypothesis, not a conclusion, a first chapter, not a last. It is worth being precise about what we know, what we think we know, and what we do not know about K2-18b, because in the excitement around this story, those categories have sometimes been treated as interchangeable, and they are not. What we know. K2-18b exists. It is in the habitable zone of its star, and James Webb has confirmed methane and carbon dioxide in its atmosphere. Those detections are robust, confirmed by multiple independent analyses, and consistent with a water-rich world. What is inferred but not confirmed, that K2-18b is a Hycean world with a deep liquid water ocean. This interpretation is consistent with the data. It is not the only interpretation consistent with the data. The planet could be a rocky world with a thick steam atmosphere, or a mini Neptune with no liquid water at all. What is contested? The presence of dimethyl sulfide or dimethyl disulfide. Some analyses see it, others see noise. The difference between those outcomes depends on decisions made at the instrument calibration level. Choices about how to reduce the raw data that different research groups are making differently and getting different answers. What is unknown and may remain unknown for some time? Whether JWST has the sensitivity to deliver a definitive answer about this particular molecule on this particular planet. That answer may require an uber-sophisticated telescope, one that does not yet exist. The scientific community is currently divided into at least 3 distinct positions on K2-18b, and it is worth understanding each one clearly because each has legitimate scientific backing. The first position, the DMS signal is real. It is at 3 sigma. It matches predictions for a Hycean world, and when additional JWST observations are obtained, the signal will confirm to 5 sigma. The planet may harbor a biosphere. The correct response is to secure more telescope time and move carefully toward confirmation. The second position, the MIRI instrument is producing instrumental systematics in the mid-infrared range. Essentially, the instrument is creating artifacts in the data that look like molecular signals. The DMS detection is noise, not signal. Further JWST observations of K2-18b in this wavelength range will not resolve this unless the instrument calibration issues are fully understood and corrected first. The third position, the DMS question, may be unresolvable with James Webb, regardless of how much observation time is devoted to K2-18b. The molecule's spectral features overlap with other molecules. The instrument was not designed for this sensitivity, and the planet may require direct imaging, blocking out the star's light entirely and studying the planet's reflected light, which requires a telescope that will not be available until the 2030s at the earliest. Under this view, K2-18b is the right answer to the wrong question, asked by the wrong instrument at the wrong time. None of these three positions is without scientific credibility. The question is not which side to believe. The question is, what kind of evidence would force a resolution? And that question has a sobering answer. There are, as of early 2026, more than 5,000 confirmed exoplanets. Of those, somewhere between a few dozen and a few hundred are in habitable zones of their stars. Of those, a handful have the size and composition profile to be ocean worlds. Of those, K2-18b is currently the most studied, the closest, and the most controversial. The Milky Way contains an estimated 200 to 400 billion stars. The best models suggest that most of them have planets. If even 1% of those planets are in habitable zones, we are talking about billions of worlds. The question of whether life is common in the universe cannot be answered by K2-18b alone. But K2-18b is right now the most credible place to begin asking it. K2-18 is an older star than our Sun. The system has had more time for life to emerge and evolve, if the conditions have been right. Earth took roughly 700 million years to produce its first microbial life from lifeless chemistry. If K2-18b has been wet and warm for longer than that, the question of whether life has had time to begin is not a barrier. Time is not the problem. For 3 billion years, the dominant life form on Earth was microbial, simple, single-celled, producing gases, reshaping chemistry, surviving conditions that would kill anything complex. If K2-18b has life, it is almost certainly microbial, small, ancient, and chemically productive, and even microbial life would be one of the most significant discoveries in the history of human life. The implications of life on K2-18b, if confirmed, would extend far beyond astronomy. The most immediate implication would be statistical. If life independently emerged on a second planet, even microbial, even simple, then life is almost certainly not rare. It is probable. It is perhaps inevitable wherever conditions allow it. All life on Earth shares a common ancestor. Every organism that has ever existed on this planet, every bacterium, every plant, every animal, every human being, traces its origin back to a single chemical process that began in an ancient ocean somewhere between 3.7 and 4 billion years ago. If K2-18b has life, it began separately, an independent second origin, and that changes everything. It would also mean that we are not searching for a needle in a haystack. We are searching in a field where needles grow. NASA's proposed Habitable Worlds Observatory, currently planned for launch in the late 2030s or early 2040s, is specifically designed to do what JWST cannot: directly image Earth-sized planets in habitable zones and capture their atmospheric spectra with far greater sensitivity. It will not be limited to the transiting method. It will look at planets directly, blocking out their stars, and read their atmospheres in light that has been reflected from their surfaces. If life is there, it will find it. On the ground, the extremely large telescope, currently under construction in Chile and scheduled for first light in the late 2020s, will use direct imaging methods from Earth's surface to characterize exoplanet atmospheres with resolutions not currently possible. The pipeline from K2-18b's contested signal to eventual confirmation or refutation runs through instruments that are being built right now by people who have been changed by this question. The debate over K2-18b has accelerated the development of biosignature standards. The scientific community is now actively building frameworks for what constitutes evidence of life, not just a molecule, but a constellation of independent data streams that together make the case too strong to dismiss. K2-18b, whether its signal is real or not, has made that framework necessary. Professor Madhusudan has spent years on this problem. He proposed the Hycean planet category. He identified K2-18b as a prime candidate. He pushed for time on the James Webb Telescope, and in April 2025, when his team saw the 3 sigma signal for DMS, he described the moment carefully. Cautiously optimistic, he said. Not certain, cautious, but optimistic. The scientists who push back on K2-18b's signal are not pessimists. Kevin Stevenson, who concluded that the DMS detection does not meet the standards of evidence for life, has been clear that K2-18b remains a fascinating world. His objection is to the strength of the claim, not the importance of the question. Science needs both the searchers and the skeptics. The two roles are not in conflict. They are the same method, applied from different directions. Somewhere right now, a graduate student is writing a dissertation on K2-18b. A postdoctoral researcher is reprocessing JWST data for the 5th time. A theorist is building a chemical model of a hydrogen-rich ocean to test whether DMS can form without biology. The machinery of science does not stop because the headline fades. And somewhere, someone who heard about K2-18b last April and felt something shift inside them, some quiet reordering of what they thought the universe contained, is still thinking about that feeling, wondering if it was warranted. We began with a star, a small, cool, quiet star in the constellation Leo that most of humanity never knew existed. We are back at that star now, but it is not the same star it was before. The question has not changed. We still do not know if K2-18b harbors life. But what has changed is what that question costs us, emotionally, scientifically, philosophically. The scientists who believe the signal and the scientists who doubt it are both correct about something. The believers are right that the evidence is worth taking seriously. The molecule is there, the statistics are real, the world is in the right place for life. But the skeptics are also correct that the evidence has not yet crossed the threshold that science requires before calling something a discovery. Both of those things can be true simultaneously. That is where we are. We are using the most powerful telescope we have ever built, pushing it past what it was designed for, to look at a world it was not designed to study, for a signal it can barely detect. And even so, there is something there. Whether that something is life, or chemistry, or noise, we do not yet know. There is a question that follows from K2-18b that has nothing to do with spectroscopy or sigma values. It is the question that the discovery would make unavoidable. Life on Earth exists in conditions that should be impossible. In the crushing darkness of the deep ocean, in volcanic vents that would melt most materials, it is persistent, inventive, and ruthless in its ability to find a foothold wherever chemistry and energy intersect. If K2-18b has an ocean, and if that ocean has liquid water, and if the chemical building blocks are present, carbon, hydrogen, nitrogen, oxygen, sulfur, then the only question separating us from the answer we want is whether the universe needed to try this experiment only once on a pale blue rock orbiting an average star in the outer reaches of an ordinary galaxy, or whether it tries it wherever it can. If the answer is that the universe tries it wherever it can, then this galaxy, this single ordinary galaxy in a universe of 2 trillion galaxies, is not mostly dead space with a few isolated exceptions. It is a living system, distributed and ancient, and we are not alone in it. That thought is not comforting or alarming. It is simply enormous. We have been reaching upward for as long as we have been looking up, toward warmth, toward light, toward whatever is out there that might reach back. K2-18b has not answered that reaching, but it has made the question feel closer to answerable than it has ever been. 124 light-years is not far by cosmic standards. The light leaving K2-18 right now will reach Earth in 124 years. Whatever is happening on K2-18b at this moment, whatever chemical reactions are occurring in that ocean, whatever molecules are rising into that hazy sky, that information is already traveling toward us. We just cannot receive it yet. Somewhere in that ocean, if it is an ocean, there is either life or there is not. That sentence has never been so close to being testable. We are one telescope generation away from knowing, perhaps less. This is our world and beyond, where the science is real, the questions are open, and the universe continues to be larger and stranger and more full of possibility than we can even imagine. If this film sparked your curiosity, subscribe so you're here for the next deep dive, every Friday at 6 p.m. Mountain Standard Time. Leave your thoughts in the comments. The question of life beyond Earth is one we're all living through together, right now, in real time. We'd like to keep exploring it with you.